A Markov process is a stochastic process that has the following property. So this is the part 2 of the part 1 that concern a very brief introduction of stochastic processes with some definition of what is the Brownian motion and an approximation. So now in this part 2 I would like to define and introduce what is a Markov process. So suppose we have at a discrete point x1 at time t1, x2 at time t2, and so on, xn at time tn. We have a collection of events, and the probability density function is the following. So the probability that x at time tn is located at position xn, so in the volume dv, and then condition that at time tn minus 1 the point was at position xn minus 1, and so on, x at time t1 was at position x1 plus dv. So we say that this process has the Markov property when this conditional probability can actually be reduced to the probability that xtn is at xn plus dv, condition that xtn minus 1 is at position xn minus 1 plus dv, and that's it. That is, the history of the process, which started at position x1 at time t1, and then there was a jump, position x2 at time t2, and so on. So we have now xn minus 1, tn minus 1, and xn tn. The probability of such a transition here is actually independent of all previous transition. So this is the characterization. So this is an important to characterize. So this, all the history here can be forgotten, and only the last step is important for calculating the transition probability. So this ensemble of processes, which are called Markov processes, are important because many physical, biological processes fall under these rules. Associated to this definition, there is a direct consequence, and the consequence are called the Chapman Kolmogorov equation. So I would like now to introduce this equation. So the Chapman Kolmogorov equations for a Markovian process. So this starts with the Bayes law, which is again one of the very important and fundamental laws that is used everywhere in probability, which says that if we look at the probability of a joint event that we characterize and we denote by A and B, so the probability to have A and B can be written as the probability to have start with B multiplied by the conditional probability that, knowing that we have B, we have A. So, and this is by definition the equals to the probability, according to Bayes' law, of the probability of having the joint event A and B. And of course this can be written also, because it's symmetric, as the probability that if we start from A, then to have A and B we need to use the conditional probability to have B condition on A. And this is the probability, which is the same of the two events B and A, or A and B, which are the same here. So we're going to use this in this what is called the strong Markovian property that we have defined before for the following calculation. We would like to look at the probability transition function. So suppose we start at position x and time t, and we look at the rival that the process is, let's say, located at position y at s. And then we are going to introduce an intermediate step, which we write it as z, position z, and the time r, such that we have by definition t is the initial time, is less than r and less than s. So or maybe let me do it the reciprocal. Suppose we start, so this is the position z and r, and suppose we go in this direction, we start, this is the starting point and this is the end point. So then what is the probability that, so the initial point is y and s, the condition that we started in here, the process went into the position z and r and then to the position x and t. So to calculate this quantity, we are going to use the base formula that is just written here. This is the probability that we started at position x and t, condition that it went into zr, and before it was in y and s, multiply by the probability of such event, which is the probability of z and r, condition on y and s. So now, using by definition the strong Markov property, we can get rid of the past, knowing that this is the latest event. So this can be rewritten as the probability to make a transition to xt starting from z and r, and then multiply by the probability, which is the next term, which is here, the probability that the trajectory arrived at z at time r, condition that it started at y and s. So this is the expression for this quantity. And now what can be now what we are interested in is to look at the probability of making a transition from y and s to x and t. So by definition, we can go from this stage, so we can start in y and s, and we can average over all intermediate position z and r, and we end at x and t, and this we have to integrate over dz. Right, so this is the and we integrate over z in the space. So this is exactly the transition probability. To start in this, we introduce an intermediate point, and the last point is this one. So now, using exactly the calculation that we have done before, then we obtain that this is the integral of a z of the probability to make a transition from ZR to X and T multiplied by the transition probability from Y and S to ZR. So this is by definition the Chapman Kolmogorov equations. And for example, it is possible to check, and I will leave this as an exercise. It is possible to check that the Brownian motion give us this has this property. Before I'll discuss some references. So I think the second exercise will be to show that the probability of switching from let's say Z and U to the probability to switch from Z and U and Y and S, so to X and T, this is simply the probability to go from to arrive in X and T starting exactly at Z and U. So this has to be proved using show this using the properties of the Gaussian integral, using the classical properties of Gaussian integrals. So again, the way to do it, just this is a hint. We can start. We have to start with the following expression. This is 4 pi d t minus u square root exponential of z minus x squared divided by 4t t minus u, and this has to be written, this term, so this is what we need to find, and this has to be written here in terms of two integrals, and I leave this as an exercise for the reader to show that the Brownian motion satisfies actually the strong Markovian property. And so I just would like to come back to some classical references about stochastic processes. The classical book is Carling and Taylor, first and second course of stochastic processes. And also I'll mention the book of Schuss. There are the two books. One is from 1980, Theory and Application of Stochastic Differential Equation, and the more recent one in Springer about Theory and Application of Stochastic Processes. So this is again two crash course, some of a very basic introduction about Markov processes and this Chapman Kolmogorov equation. And in the next class we will introduce stochastic equation and how to manipulate them.